Okay, this is the second half of my lecture for today, and this is my first look at the group operation on elliptic curves. So, just as a reminder, we have the graph of an elliptic curve. That graph is the set of all x, y coordinates that solve my equation. Y squared equals x cubed plus ax plus b. The a and the b here are some constants, so I can vary the parameters and I can get lots of different elliptic curves. All of them are elliptic curves, just the same as all parabolas are parabolas, just with different formulas. And all of them have group structure, at least as long as we don't have a zero discriminant. You can check my previous lecture for that. So the elements of my group are going to be the points on the graph, right? Here is one of my graphs again. Let me zoom back in to get that more familiar shape. There it is. So there's my sort of horseshoe-looking elliptic curve. And I can imagine the points as x, y coordinates, and I'll use lowercase letters for x and y. But since this makes up one of my group elements, and since I'm thinking about doing geometry, I'll also be using the geometry notation of just using a single capital letter to indicate a single point on the graph. So sometimes I'll be using x, y coordinates, sometimes I'll be using capital letters. I need to explain how is it that we take two different points on the elliptic curve, add them together, and get another point on the elliptic curve. So, what structure do I already know about the elliptic curve? What is already here that I can take advantage of for defining my group operation? Well, number one, we saw in my previous lecture that every single elliptic curve has a mirror symmetry through the x-axis. So what we have above the x-axis is exactly what we have below the x-axis. I can just mirror across this line. Get rid of that. Get rid of that. I can just mirror across this line and I'll have exactly the same graph. So that is one geometric fact about this elliptic curve, and we are going to take advantage of that for our group operation. And part two, from the first half of this talk, all elliptic curves have a point at infinity. In fact, it's the same point at infinity for every single elliptic curve. It's the point at infinity for vertical lines. Okay. So this point at infinity is going to be special, and I'll give it the name O. So I've written it in a kind of a funny font here because it's that important. And I don't have x, y coordinates for the point at infinity because it's not in the plane, right? Points at infinity are just sort of in our head. They are nice to imagine. They make certain geometry problems easier to think about. But it doesn't exist the same way that an xy coordinate pair exists. So I got to give it some name. I'll just call it O, or I might say script O because I'm using a funny font here. So the point O is going to end up being the identity element of our group. This is really handy because I know every single elliptic curve runs through the point at infinity, O, or you might think of it as O is at the very end of the elliptic curve. But since it's the same point every single time, I may as well just say this one is the identity, and that'll be nice because then I know that all of my elliptic curve groups have the identity element. Does that make sense? It's a little back to front because I'm still trying to explain how the group operation works. But the idea is that my point P plus the point at infinity will always have to get me back to P, right? Because that is what it means to be the identity element. So I've used one of the useful things about my elliptic curve here. I've used the fact that the elliptic curve meets up with a point at infinity. I have not used the symmetry yet. So how can I use the symmetry? I'm going to use the symmetry in the graph of the elliptic curve to define my inverses. So elliptic curves are usually written where the group operation is addition, right? I take 2 points, I add them together. That means that my inverse elements have to use subtraction, right? That's just sort of the convention that we use. The opposite of addition is subtraction. So if I have a point P whose coordinates are x and y, its inverse is going to be minus P, right? P plus minus P should be 0, right, if we were doing regular addition. So in this case, P plus minus P should give me O, the point at infinity. The coordinates for minus P are going to be the only other point I can guarantee is on this curve. So if I know that P has coordinates x and y, and I know that the elliptic curve is symmetric, right? It has that mirror reflection, I can guarantee that the coordinates x and minus y will also be on the curve, right? So x and y solve my equation, y squared equals a cubic in x. Well, it happens to be that minus y squared, squaring a negative number gets me the same thing, so these coordinates will also solve the equation, which means that these coordinates are also describing a point on the elliptic curve. This is the only way I can guarantee having another point if I don't know what my formula is, right? I might not know what the number A is. I might not know what the number B is. It doesn't matter. If x and y is a coordinate on that curve, then so too is x and minus y. It's a pretty pragmatic choice. So the question, what makes this choice special? What makes P and minus P special? Well, what does that have to do with the point at infinity? If I think about it, the coordinates for minus P are just what I got from taking the coordinates of P, and they actually have the very same x coordinate. Let's take a look at how this plays out in my graph. So same graph, same elliptic curve. I've got my bulb back. Let's go ahead and look at this point right here. So x equals about -1, y equals about 2. So this is a point on the curve, and here is its negative. Remember that I am negating just by flipping the y coordinate, and I keep the x coordinate the same. Because these 2 points have the same x coordinate, I can draw a line through them. That'll be here in green. My graphs are doing double duty now. And the line that I draw between them will always be vertical. Because they have the same x-coordinate. Two different points with the same x-coordinate, the line between them has to be vertical. Well, hang on a minute. Vertical lines are where I got this point at infinity business to begin with, right? I know that if I zoom out and zoom out and zoom out and think about what I would see, not looking down at the plane, but actually standing here and looking out at the horizon line, that this vertical green line that I got from connecting two points is going to end at a point at infinity, and that point at infinity is also going to be where my red elliptic curve meets. So, zooming back in for a bit, I pick 2 points on the curve, I draw a line between them. It happens that this is the point P, this is the point minus P, and way out in the distance, this line hits a third point belonging to the elliptic curve, and it hits the identity. It hits the point O. So this is a very important idea for working in elliptic curves. Our group operation is based off of drawing lines between two different points of the curve and seeing where else it hits. Because of that relation, if I take any point here, right, here's the point x equals 3, y equals 4. Here's the point x equals 3, y equals negative 4. Let's draw a line between them. That's a vertical line with the formula x equals 3. So there's my vertical line. And I know that the green line and the red line, the actual line, not the elliptic curve, these are going to meet at a point at infinity. They're going to meet at the same point. So this point plus its inverse gets me the point at infinity. This other point plus its inverse gets me the point at infinity. So this gives us a very easy way of calculating the inverse of any point. Okay, so I am a little short on time to define how to add arbitrary points together. I will be covering that on Tuesday. If you want to spoil yourself, there's plenty of other videos on YouTube where they talk about the elliptic curve group. But I will be going over it in my own way next week. Please, for today, make sure that you have your brain wrapped around the point at infinity and this idea about intersecting lines with an elliptic curve in order to do our group operation. We'll continue developing this material next week before we get on to actually making this useful in a cryptography setting. All right, I'm looking forward to that. I hope you have a great weekend.